So hello everyone and welcome for this last week. It's week 8 of the course of networks. And today what we're going to be doing is to focus on a very topical issue, which is the problem of modeling epidemic processes. And we'll see how the use of networks may help to improve modeling. But just before we start, I just wanted to spend a few slides to motivate the importance of this problem. So you've clearly seen in newspapers over the last year or so that many researchers are developing models that basically try to understand what has been happening in the past in terms of epidemics, and to use that past information in order to predict its future outcome. And the design of efficient methods has been a very central tool that policymakers can use in order to design some efficient policies that may help to prevent the spread of the disease and to control it, basically. Now, there are many different types of models that exist, and here you can see, for instance, a comparison of the outcomes that would have been generated by a certain number of models in May of last year. And you see that there is quite a bit of variability in their predictions, and that comes from the fact that these models tend to be based on different data often, but also on different modeling principles. Now, when you think about the modeling of epidemic spreading, the most simple framework would be the one of the mean field. And we're going to be describing these models in the next video. But in essence, what we think is that all of these social agents can mix, and through their interactions can basically propagate the disease. This is clearly a very strong assumption, and this could maybe happen if you consider people who might be in a closed room, for instance. But at the scale of cities or countries, this is clearly a bad hypothesis, a bad assumption. And it's clear that there are pairs of people who may interact because of their closed physical proximity, while others are extremely unlikely to have a physical interaction in a certain period of time. And one way to try to alleviate these limitations is to incorporate some network modeling into the epidemic process, and to use networks that basically constrain the way by which agents can interact with each other or not. Now, indeed, and this is something that we've seen already in a previous slide, if you have information about contact networks, for instance, here is an example from an article on the chains of affections. That was basically a paper where the authors investigated the sexual relations that students of a high school have had during a certain amount of time. And what we notice is that clearly the network structure can have a big influence on the kind of epidemic process, in this case of sexually transmitted diseases, that may happen in the system. And here the existence of a large connected component implies the possibility for a large outbreak to be observed in that school. Now, the problem is that, of course, you can, by interviews, for instance, and hoping that the people tell the truth, you can hope to measure contact networks in small environments. But the problem is that when you confront it to a disease like COVID-19, for instance, you need to do that at the level of countries. And it becomes a challenge of its own to be able to estimate and to measure the contacts that are basically happening between the individuals. Now, one way to do so is to use, for instance, tracking devices or like mobile phones that would be using Bluetooth technology. But even by doing so, you have a lot of uncertainties in the way you estimate these contacts, because typically you need to make a choice and decide that you're going to be having a contact when the people are at a certain distance X during a certain period of time T. But depending on those parameters, you will basically have some variability in the estimated networks. Even more so, an issue is that these networks that are typically taking place are not static networks like the one that I did before, but they are highly dynamical. And it's not clear that the contacts that I have today or yesterday or tomorrow will be the same, which basically means that you also need to take this kind of temporal variability into account in principle. Now, typically, if you have a network and you can observe the past contacts, well, of course, this will not be useful for the modeling, but this is still something that can be very helpful in practice. And this is by essence what people are trying to do when they do contact tracing. So you heard a lot about contact tracing. You know that when someone basically shows symptoms and is discovered to be positive to a certain disease, well, basically the idea is to do some contact tracing to try to find all of the contacts that that person has had in the past in order to contact them before they can themselves infect another person. And this is something that can be done by means of mobile phones, for instance, with Bluetooth, or it can be done with by phone calls, by investigators who call someone and ask the list of contacts that he's had in the past. And actually in this paper, they show the importance of being able to do this contact tracing in practice. So here what you have is this number, this famous reproduction number that you've all heard of before. You know that when the reproduction number is larger than 1, you have an exponential growth of the number of diseases. When it's smaller than 1, you have an exponential decay. Yeah? What you want to do as a policymaker is to try to reduce this reproduction number by all means possible. What they show here is that actually quite a large part of the reproduction number comes from pre-symptomatic people, people who have the disease and have not had yet the time to develop it. Now, if you can contact these people before they have the symptoms, because actually, and you can find them because they had a contact with someone who was declared to be sick, then it allows you to reduce this number that is quite large, and hence to reduce quite drastically this reproduction number. Now, this is an application of what you can do from the past contacts, right? And these are the contacts that you can measure in principle. But what about the future ones? Well, for the future ones, obviously, this is much more difficult. And there you need basically to have some sort of a model that tell you what would be the contacts that you have in the future based on those that you have in the past. Well, one way to do so is to forget completely about the temporality of the graph and to assume that the temporal graph is constant. And this is the simplest assumption, and this is what we're going to be covering today. But there might actually be more complicated models that try to account for the inherent temporal variability that may be observed in social networks. So this is one way by which networks can be useful in order to improve epidemic modeling. Another way by which it can be improved is much more coarse-grained, and it comes really from this observation that measuring the contacts between any pair of people in a population is extremely difficult and actually unrealistic in practice. And hence, maybe that instead of focusing on each of the people as nodes and their contacts, the contacts that they have, what we could try to do is to try basically to divide the map into regions and to try to estimate what would be the flows of people between these regions. And if you make the assumption that the people may carry the disease, it may help you to understand how the disease is going to be propagating spatially. Now, this is actually something that people have been doing for quite some time, but there was a very nice paper from a few years ago, from 2013, where two researchers looked at the way SARS basically invaded the world at the time. And SARS first originated in China. And what they wanted to do was to estimate when was the first time that the disease was observed in a certain country, and to try to find a variable that explains when is the first time that the disease appears in a country. The first natural choice for this explanation would be physical distance. But if you show this time of the first occurrence as a function of the physical distance, well, you see that there is a lot of noise and there is no clear signal. Now, if instead of looking at the physical distance, you look at the same relation, but now you measure the distance in terms of networks, and here you would have that you start from China and you look at the network of flight connections that start from China and go to other countries. Well, that gives you a graph. In that graph, you can measure a measure of distance between the origin and a certain destination along the shortest path. And from there, you can estimate an effective distance, a graph-based distance between one country and another one. And if you now plot this time of the first occurrence of the disease with respect to this effective distance, you see a very nice linear correlation that clearly suggests that networks may be a good framework, may be better than just spatial modeling if you want to understand how diseases spread spatially. Now, as we'll see, there are ways to incorporate this observation into a modeling. And this is something that we'll be doing also in one of the next videos. And this is a framework called metapopulation models. So basically in a metapopulation model, what we do is we're going to be considering that the nodes are now basically populations, and they may be corresponding to cities or countries, for instance. The links corresponds to the flows, and they are typically weighted flows, and they tell you what are the pairs of cities where there are some certain large values of exchanges of population in a day, in a month, depending on the data. And what you do now is you are taking this graph, showing you the connectivity between different regions in space, and you will have that what is diffusing on that graph would be people. And what you will be assuming is that once people are inside a certain population, they interact in a mean field fashion. And by this combination of mobility and interactions inside the populations, well, you have a model that actually can also be fitted empirically, and that allows you to have something that is relatively simple mathematically, but yet much more rich than a simple mean field model. But we'll look at that model more in detail just after. Now, just as a summary, what are we going to be doing this week? Well, we will be looking at models for epidemic spreading, and we'll start by looking at the mean field scenario before looking at metapopulation models. These are the ones that I just described before. And finally, we'll be looking at situations when we are given the exact contact network inside the population, and we try to use this contact network in order to predict how certain diseases would be spreading inside it. So, well, I hope that you're going to be enjoying this last week, and I welcome you to watch the next video. So in this second video of the week, we'll be describing the most basic models that exist for epidemic processes. And we're going to be describing them and looking at certain of their properties in the mean field. So when you try to model some epidemic spreading, well, the most common approach is to use compartmental models. So compartmental models. And in compartmental models, you assume that your population is composed of agents that are interacting with each other. And these agents can be in different states. Those would be different states associated to the disease. And these states can be seen as compartments. Now, depending on the kind of states that you have and on the different types of transitions that the people can have from one state to another one, you typically have different types of models. So there are typically the most common compartments or states that exist would be the state of S, to be the fact of being susceptible. There would be I, to be the state of being infected. And there would be the state of R, that would be the state of being recovered. And that would be the case, for instance, when you develop antibodies. And even if you come into contact with an infected person, you cannot be infected anymore. And so, as I said, in models like those, you're going to be looking at the dynamics of the densities of the population inside some of these states. Now, the three most common models are SIS, where basically you can start from being susceptible, become infected, and become susceptible again. Then there would be SIR, when you would be susceptible and then possibly become infected, and after that recover. And the last one being SI, you're susceptible and then you may become infected, and once you're infected for all times. Now, for all of these models, the most simple way to analyze them and already to have some sort of a qualitative understanding of its properties is within the mean field. And in the mean field, basically, we assume that we have a certain number of agents. And these agents are basically interacting completely randomly in the course of time, and any pair of agents is equally likely to interact. So let's have a look at the kind of equations that this gives us. And let's start with the SIS model. So here in the following, we're going to be using S of t to denote the fraction of susceptible agents in the population, and I of t to be the fraction of infected agents in the population. Yeah. And clearly, what we need to have in principle at all times is that S of t plus I of t is going to be equal to S of 0 plus I of 0, which by definition is equal to 1. Now, if you want to write down an equation for the time evolution of these quantities, well, you very easily obtain the following equation. So we have minus beta, then we have almost done. So what does it mean? It basically means here that, okay, so the process is defined by two rates, a rate beta and a rate mu. And with a rate beta, basically, when we have interactions taking place between, if we have an interaction taking place between an infected and a susceptible person, the susceptible one would become infected. So it means that they're going to be leading to an increase in the number of infected people and a decrease in the number of susceptible. But you also have the possibility for the infected people to recover, and this happens with a rate mu. Now, if you write down the equations that are associated to that, well, you arrive at this, where you would have here that the way the number of infected people changes in time increases proportionally to this rate beta and to the product of the fractions of infected and susceptible people. Yeah. Now, you will also have, because you need to have to select basically one of each for an interaction to take place. But at the same time, you have also the possibility for the infected people to recover, and this happens with a rate mu. And you have the minus sign of these two quantities for ds by dt in order to make sure that d by dt of S of t plus I of t is equal to 0, and thus that we verify this conservation rule that is necessary. Now, here, typically what we are interested in the situations when what would be the asymptotic state of an equation like this one. And actually it can be shown that, well, it's going to go to a certain stationary state. And this stationary state, noting that the I of t, that S of t is equal to 1 minus I of t, well, it's going to give us the following condition. We'll basically have that I star, that would be number of infected people at the stationary state. And then we'll have beta times well, S star minus mu is going to be equal to 0. Yes. Which basically means here that, well, first of all, we have two possibilities for this to be satisfied. The first one is that I star equal to 0 is always a possible solution. Yes. So having exactly 0 infected people is indeed always a possible solution of the problem. Now, for the other solution, we need to look at this fact here. And if you replace S by 1 minus mu, basically it's going to be implying that we need to have the I star is going to be equal to 1 minus mu divided by beta. And so it means here that the total number of infected people, well, clearly is going to be is going to be increasing in situations when the rate beta becomes larger, which is quite expected. Now, there is just one condition here, is that this I is a fraction. It needs to be a positive number, which basically gives us a solution for this second solution to exist. We need to have that beta divided by mu is going to be strictly larger than 1. Yeah. And so it means here that, well, when the beta of mu is going to be smaller than 1, the solution that we'll have is going to be I star is equal to 0, and this will be the only solution. And if you look at linear stability analysis, we'll have that beta over mu, when it is larger than 1, we have a transition. And that basically happens when the rate of infection becomes too large. The I star equal to 0 becomes unstable, and we get as a solution I star is equal to 1 minus mu divided by beta. And we see here that there is a threshold below which there is no epidemics, and above which we have a stationary state where the number of infected people remains non-zero, and we have an endemic state for the disease. And so we have this critical transition between no infection and an endemic state. Now, this is what we can do for the SIS. So actually, let's just have a look at what would be happening for the SIR. So in the case of the SIR, well, let's have a look here. We also have a rate beta for the interactions, but now with the rate mu, we'll have that the infected node basically goes into a recovered state. And this recovered state, once you reach it, you are basically excluded from the dynamics. So now the kind of dynamics that you would have now would be the following. So we'll have d by dt of s of t, then is equal to minus beta I of t times f of t. And then we'll have di by dt times, of I of t, is going to be equal to beta I of t s of t minus mu I of t. And the last one being dr by dt of t is equal to mu I of t. Now, the kind of dynamics that you have here is quite different from the SIS, because in the SIS you could reach a dynamical equilibrium where you would have a finite fraction of infected people would be remaining constant in time. While here actually it can be shown that asymptotically the system basically reaches a stationary state when there is no infected people anymore. And you arrive in a situation when you only have susceptible and recovered people. And this total number of recovered people tells you how many people have been infected in the past, basically. Now, it means that typically when you do this analysis, something that is quite important is to understand what would happen if you started from a fully susceptible population and we just put a tiny fraction of infected people. What would happen? Would this tiny fraction of infected people disappear? And so it means that that would lead to a stable situation where everyone is susceptible. Or would it be exploding, in which case the state of everyone susceptible would not be stable anymore? Well, actually, this is precisely what the kind of analysis that is done. And what people tend to do typically is to consider the equation here, yes, and to look at it in the situations when in a linearized situation. And if you do it in a linearized situation, you're going to be assuming that the S of t is equal to 1 plus something very small. Yeah? And if you actually look at d by dt of I of t, it's going to be behaving like beta I of t minus mu I of t. And you will be able to show that actually you get exactly the same kind of change of behavior. If the beta of mu is larger than 1, you're going to be having that initially you have an explosion in the number of infected people, while if the beta of mu is sufficiently small, below 1, you're going to be having that a small perturbation is going to basically be absorbed and the number of infected people will disappear. Yeah. And so it means that we see that in each of these two models, we have the existence of this threshold above which you have an invasion of the population, below which you don't. So just very rapidly before concluding this section, I just wanted to mention the SI model. So again, in the SI model, you get something quite different. In the SI model, basically, and let's have a look here, you only have the possibility for the infection. It means that you only have infections taking place. So it's clear that if you have a graph that can be seen to be connected, where everyone is interacting with everyone, well, asymptotically, we can be sure that the total population is going to be infected. So it basically means that in the case of the SI model, what is actually important is to understand what is the approach towards this fully infected state. And if you're interested in this regime where you approach this fully infected state, well, again, you can write down equations before, and they take a shape that looks very much like the previous ones. You're going to be having beta times the S of t times the I of t, yeah? And there is no minus sign, there is no possibility for recovery now. And, well, clearly, if you assume that initially the S of t is of the order of 1, what will happen is that initially we'll have that the population is going to be growing like exponential of beta times t, yeah? Which basically means here that here we're going to be having that this infection rate tells us about how initially is the number of infected people growing in time. Now, as I discussed in the first video, well, here we have three models for epidemic spreading, but the three of them assume a full mixing, the fact that all of the agents are interacting with each other, and this gives us two equations having a form like this one. So as I said, this is something that clearly is invalid in situations where the population is too large and there is not the possibility for any pair of nodes to interact completely uniformly. And that's the reason why in the next two videos we will be looking at two ways to generalize these models by incorporating a certain network. So indeed, so as I said, so in the last video, we've been looking at epidemic models in the mean field. And today what we're going to be doing is to look at one way to improve on these models by incorporating some network information. And the way that we're going to be doing is by means of metapopulation models. So in a metapopulation model, what you have in mind is that your space is basically can be divided in different entities. And these entities, depending on the data that you have, on the granularity that you're interested in, could be corresponding to some neighborhoods or to some cities or even to some countries. And what you're going to be doing is to assume that each of these elements can be described as a node, and that the way people travel from one place to another one can be interpreted as a weighted edge. So basically it means that you're going to be arriving at a representation of the way the people are basically traveling inside your system as a weighted graph where the nodes are the locations and the edges tell you the flow of people that go from one place to another one. Yep. Now, once you have this, basically this background, you're going to be allowing some agents to move on that graph and to interact and possibly to infect each other. And the key point here is that the people are going to be navigating the nodes, and they will be allowed to interact with all of the others that are inside the same nodes as they are at the same time. So if at some point in time you have that in a certain node, you have, for instance, one infected and many uninfected, like susceptible nodes, well, this infected node will be able to interact with all of those here in a mean field way. And so clearly this is an improvement over the mean field. You don't do the mean field in the whole population. You just do it in the local populations, and you allow for this mobility for the people to basically explore and diffuse across the different locations. So let's try to formalize that problem. So here, what we're going to be having is a certain meta-population network, meta-population network. And it's going to be made of n tilde nodes. So we have n tilde populations, n tilde locations. And what we're going to be assuming is that they are connected, and the links basically tell you about the flows, the typical flows that exist between these nodes. Now, what we're going to be doing is to look at agents that they're going to be exploring this underlying graph, and we'll basically have n agents that are individuals that will basically represent people, basically. And these people are going to be navigating the graph according to certain rules of how they travel inside the graph. So indeed, a very important aspect would be a way to encode the topology associated to this meta-population network, and the way to do so is simply by means of an adjacency matrix that you write A tilde ij, that we assume to be symmetric just for the sake of simplicity, but this could be generalized. And this here basically defines this undirected network. And the agent will be traveling on this undirected network. Yep. Now, so here, so one of the key advantages of these models that are based on subpopulations is that they provide somehow a coarse-grained representation of the way the people may be interacting. So it's not so coarse-grained where everybody is connected to everyone, like in the mean field. It's clearly less precise than a contact network where you know exactly who's interacting with everyone. But this is some sort of like an intermediate level of description where, well, you try to account for something that you know, the fact that when people are located at the same place, this allows for the interactions to take place between them. Otherwise, there is no chance that they interact and infect each other. Now, so here, basically, so when you consider a metapopulation model, there are two ingredients that you need to define. The first one would be, what is the mobility? How do the people move? So the first key aspect now is basically to decide what would be the rules for the mobility. And indeed, we have these agents that are on these locations, but how do they explore the graph? What are the rules that determine that? So in practice, if you have empirical data, you could fit this to empirical data, yes. But here, what we want to do is to find a simple model for which we can derive certain analytical properties. So we're going to be taking a very simple assumption where basically we'll be assuming that all of these agents are performing a random walk. So it means that the agents are random walking this space of locations, and where the space of location is encoded in this undirected graph here. So this is clearly a very strong assumption and very unrealistic one. I think that all of us agree that I am not a random walker in my motion. You are probably not. Each of us move for a certain purpose. Each of us moves for in order to serve certain goals with a certain regularity. Actually, if you look at my past mobility patterns, you can predict quite well my future ones. But this is fine. This is like the Poisson model for time series. This is clearly unrealistic, but then you could build on that in order to improve and to get more complicated and more realistic models. So here, we're going to be taking some sort of like a first order approach where we assume that the agents are random walkers. And they basically do their random walk in continuous time. Now, what would be the equation of motion for those? Well, if I write Ni to be the number of agents on node I, on location I, Well, we know from what we've seen before that the way this evolves is d by dt of ni of t is going to be equal to minus d, where d is the rate at which the walkers move, times a sum over the j's of nj of t times the L tilde, where the L tilde is simply the Laplacian that is associated to the network of the between the metapopulations. Yeah. So, well, given this, well, and assuming that the graph is undirected and well behaved, we know that asymptotically, if we let the process run for a sufficiently long time, we're going to be reaching a stationary state where the stationary density of walkers on location I is going to be proportional to the degree of node I, and this degree that we write Ka tilde is simply obtained from the sum of the j's A j tilde. Yeah, it tells you about the connectivity of a certain place. And we'll have the number of walkers on a certain location is going to be equal to this key I star. And then it's simple to show that this is going to be times n, and I just need a bit more light, divided by the average of k tilde, the average degree inside the graph, times the number of locations. Where what is n divided by n tilde? This is actually the average population density in the graph. It means here that if we let the process run for a sufficient long time, we would basically have that density, this stationary density. Cool. So that's for the first rule about the mobility. And then on top of that, we need to decide about rules for the interactions. And here, as I said, we'll be assuming that if at a certain point in time, so we have a certain number of susceptible nodes and a certain number of infected nodes, well, all of these nodes that are inside, all of these walkers, sorry, that are inside this node, inside this location, they will be interacting in a mean field way. So according to the equations that we know from the mean field. Well, given this, it basically means that if we want to describe the dynamics, what we need to consider are the number of susceptible agents in node I and the number of infected people in node I, and to write down equations for those. So I'm going to write these equations. I'm sorry, it's going to take just a bit of time. They are just a bit lengthy, but they're not so difficult to understand. So let me first write them down just for a second. So we have this, so we have minus beta. Let me just put this into the light, just to make sure that I don't make any mistake. Okay. So we have minus beta, we have NSI, NII plus mu, and then we have FNII minus DS times the sum over the j's of NSJ times the Laplacian. So basically what we have here is the following. So we have that if you look at the way the number of susceptible nodes evolve at time I, we'll have first of all an interaction term where we have that interactions take place proportionally to the number of susceptible and infected nodes. Number of susceptible and infected walkers inside node I. We also have the possibility for infected walkers in I to recover and hence to become susceptible again, because here, actually, I don't know if I said it here, we will be looking at the SIS model just as an illustration. And then finally, on top of that, we have the fact that these nodes are diffusing. Now, we have very similar equations for the number of infected people at node I, and that would be here beta n s I n I minus mu n I minus d I sum of the j's n I j l j I. And here just something, so these two equations are just minus the previous one to have the conservation of the number of Walkers through interactions. But what we have here is just that I postulated for the possibility to have two different diffusion coefficients, rate at which the Walkers move. And in principle, it seems realistic that if you have agents that are susceptible or agents that are infected, they might be diffusing at different rates. So for instance, you may have that infected people self-isolate, stay home, and hence their diffusion rate should decrease, for instance. But in principle, these are just two numbers that we can modify and that we can play with. Okay, so here we have the SIS model. And in the case of the mean field, we know that we had this transition between a state where the number of infected people would be 0 and a state where we would have some endemic presence of the disease inside the population. So do we get something of the same type here? Well, here what we're going to be doing is the following. So we will be considering the situation where we'll try to find out what is this epidemic threshold by looking at the stability with respect to what's happened when everybody is susceptible. So it means here that we're going to be considering the case when most of the population is going to be in the susceptible state. Now, and so basically, it's going to imply that all of the terms of the type n I will actually be very small. So most of the contributions associated to NI will be extremely small. Now, the thing is, as long as we have that the number of susceptible nodes move, what will happen is that we can assume that after a certain amount of time, we'll have that the NS star will actually reach the stationary state. So basically what we're going to be doing is assume that the NSI, the number of susceptible Walkers on node I at stationarity, is going to be equal to what we know from random walk theory, what I wrote just before. It would be this times this divided by the average of K tilde times the N tilde. Yeah? And now, once we have this, and that would be the dominant contribution for what's happening for the number of susceptible people, once we get this, we're going to be trying to estimate what would be the behavior of the number of infected people. And if we plug this quantity into the equation for the number of susceptible people, what we get is basically that d by dt of n I is going to be equal to beta n divided by the average of K tilde times N tilde, and then we'll have Ki tilde, and then we'll have N I minus mu, and then we'll have N I, and then plus di minus di, sorry, mu times, okay, minus, sorry, so minus di times, well, basically the sum of the j's of n I j l j I. Yeah. And so it basically means here that we are arrived at a simplified situation where we started from a nonlinear dynamics, where we have all of these nonlinear terms, to a situation now where we have a linear set of equations. And we can try to find what would be the possible stationary states associated to. Well, clearly we always have that n I star equal to 0 is always for all I in value 1 and tilde, this is always a solution. So it means that, as expected, having absolutely no infected people is always a possible solution for the dynamics. But then what's happening now is that if that's not the case, then we can look at if we are interested in the destabilization from this disease-free solution, well, then the equation will give us that d by dt of ni seen as a vector is going to be behaving like a certain matrix B times Li tilde, where basically this Bij is simply equal to, so we'll have delta Ij beta n divided by average of k tilde times n tilde times ki tilde minus mu minus minus di Lij, where Lij tilde is again the Laplacian. And it means that in principle, if you want to determine whether or not this disease-free state is stable, what you need to do is to look for the eigenvalues of this matrix here. And if you have the largest of these eigenvalues remains negative, basically this here is going to be stable. But as soon as one of these eigenvalues becomes positive, you're going to be having an unstable state, and you're going to be going away from the disease-free configuration. Now, what you would like to do is, and this is something that in principle, depending on the model parameters, can be estimated, right? If I give you a matrix, I give you the model parameters, you can calculate the matrix B and look for its eigenvalues and find out whether or not you have a stable state. Now, what you would like to do is to try to see if there is a connection with what we know from the mean field. And in the mean field, we had that this kind of threshold would be depending on this parameter beta divided by mu. Well, a situation that we can solve exactly is a situation when we assume that the di is equal to infinity. So the di equal to infinity is clearly a very unrealistic situation. It means that the infected people are diffusing extremely fast. I would be expecting the opposite, actually. But if that's the case, actually, well, then we can assume that the number of infected people in node I will be at all times equal to ki tilde ni divided by average of k tilde times n tilde, where we have that ni is the total number of infected people inside the population of n I. And this number actually, so this ni, this total number of infected people in the population, well, basically, what will happen is that in this limit, when the di goes to infinity, you can assume that infected people diffuse so fast that at any point in time, because of what we know from random walk theory, they will be in the stationary state associated to the number of infected people that we have, which is this one here. And this one actually depends on time, but it depends on time in a slower fashion than it takes for the system to reach stationarity, basically. And once you observe this, well, basically you can plug this down into your Dij, and you can actually sum these equations over the i's. And if you do so, you can directly get an equation for ni. So you can, so instead of having n equations that are coupled with each other, you sum them all, making this assumption here, and you arrive at the following expression. So if beta times n times the average of k tilde square, and then we'll have divided by the average of k tilde to the square times n tilde minus mu times ni. And clearly here we see that the condition for having an endemic state, a state that would actually be prevalent and so non-zero, so for the disease basically to survive inside the population, would be that beta divided by mu. And so it means that this state that we had here before would become unstable. This happens if beta over mu is larger than the average of k tilde square divided by the average of k tilde to the square times n tilde divided by n. And that's kind of interesting, because what does this show us? It basically shows us that the topology of the graph is going to be playing an important role. And here, more specifically, we're going to be having the fact that if we have a graph that is such that the graph of the meta population, if we have that the graph associated to the meta population is such that you have a broad degree distribution, well, in that case, we'll basically have that the k tilde square is going to be much, much larger than the average of k tilde to the square. And it will basically imply, so did I make a mistake or not? No, it's okay. And so, and basically it's going to imply that it's going to be implying that wait, so I think I made a mistake. So just a second. Yes, sorry. Apologies. I did a mistake. Sorry for that. So actually, it was not like this. It was like that, which makes much more sense from what I knew. So if you have that indeed the graph is very heterogeneous, which means that you will be having that the degree distribution is very broad and that this is going to be satisfied. Basically, this quantity here is going to be very, very close to zero. And it basically means that almost for any value of b and beta and mu, we're going to be having that the state without disease is unstable. And so it means that if you have a graph of cities that is extremely heterogeneous, well, almost independently on the parameters, you will always have that the disease is going to be surviving. So here we see that heterogeneity is actually favoring the disease. Having a high level of heterogeneity means that it's easier for the disease to survive inside a population. So of course, this is an observation that we made for this very unrealistic assumption that di was equal to infinity. Now, there are other limiting cases that could be considered. One such limiting case would be instead that we assume now that once you're infected, you don't move. Once you're infected, you stay where you are. And so we would have the di is equal to 0. Well, clearly, if the di is equal to 0, what's happening? If the di is equal to 0, and if you go back to the equations, well, basically it means that these equations here are going to be decoupled of each other, yes? And because of that, the number of infected people are going to be constrained inside a certain node. And the number of infected people grows or decays inside each of the nodes almost independently. And basically it means that in that case, you can show that the rule for the stability would be now that the beta of mu needs to be larger than this divided by the maximum degree times n. And so what does it mean? It means that in the case when you don't have any diffusion for the infected people, well, actually, you would be having that, let's assume that I have my graph, but the graph where I will have the highest, where I would basically have the highest degree, will be the one where I will have that the disease becomes endemic, while you would have that in other populations, you would not have any disease that is present. And so it means here that if there is no diffusion for the infected nodes, for the infected workers, you basically have that the infection becomes localized on the high degree nodes, while it tends to disappear on the low degree nodes. Okay? And so we see here that as soon as we incorporate some network information, well, there is quite a rich phenomenology that can occur, and that depending on the model parameters, you can have different types of behaviors. And one key challenge typically in computational epidemiology is to consider models like those, and first of all, to develop more realistic models of how the people move that go beyond a pure random walk process. And then after that, having an appropriate agent-based model to be able to fit the model parameters based on empirical data in order to be able to make predictions for the future. So, well, welcome everyone for this fourth video of the week, where we're going to be looking at another way to incorporate networks into the epidemic modeling, and that would be by means of contact networks. So in contrast with what we did just before with metapopulation models, here what we're going to be assuming is the following. We assume that we have a population, and now the nodes would be the people. And so we have now a population where the nodes are the people, and the links now correspond to the possible physical contact interactions that take place between the agents. Yeah. And as I said during the first video, well, this is clearly something that is tricky to measure, and clearly also like real world contact networks are not static. But again, as a first order model, we will be assuming that we have a network that we know without uncertainties, and that the links would basically be static entities. And here what we're going to be doing is to define the fact that for each node is going to be in a certain state, xi, and we will say that xi is going to be equal to 1 if the node is infected, and it's going to be equal to 0 if it is susceptible. And for this description of today, I'm sorry for the bad handwriting. So, and for what you're going to be doing today, we'll be looking at the dynamics of SI, this susceptible infected model. So in this susceptible infected model, what's happening? So we'll be having that when we have a pair of susceptible and infected nodes, they will have the possibility to interact with each other, and this happens with a rate beta, yes. And you will have that the susceptible node would become an infected node. And so it means here that in principle we're going to be having that the xi that are defined on all of our nodes, or they are defined as stochastic entities. And we'll be looking at a certain stochastic dynamics where described by this xi of t. What we'll be interested in is how does the average of xi of t over all of the realizations of the stochastic process basically behave in time. And given this definition of this xi, this average of xi of t can be understood as the probability that node I is infected at time t. Yeah. Now we can write down exact equations for those and for the way this quantity evolves, and that would be the following. It's going to be equal to beta times the sum over the j's of aij, and we'll have the average of 1 minus xi times xj. So we need to have an edge between I and j for an interaction to take place, first of all. But what we see is that the way the average of xi, and so the probability that node I is infected, evolves, well, actually it's going to depend on this quantity here. And this quantity is actually the probability that we have I is susceptible and at the same time that j is infected. And it is clearly the simultaneous realization where I is susceptible and j is infected, and that these two are happening together. Then we have the possibility for node I to change its state and to become infected. Now, when you look at an equation like that, well, clearly it doesn't look good, right? Well, first of all, we have n equations where n is the number of nodes. But the problem is that the way all of the average of xi evolve depend on other quantities, on higher moment of the distributions. And actually, if you try to higher order of the correlations, and if you try to write down equations for that quantity, it will also involve correlations involving even more neighbors. So it basically means here that you're going to be having a hierarchy of equations where you first have equations for the average of xi, and then you will have equations for these two-body correlations involving correlations with higher bodies, and so on and so forth. And this is a hierarchy that in principle you can write, but clearly wouldn't be something that you would like to solve in practice in a real setting. Now, this is something that happens quite a lot in statistical physics. And in statistical physics, the way to address this is to make some assumptions about these correlations. Now, there are different schemes that exist to approximate these correlations, but the simplest one, and the one that we're going to be using today, is simply to assume that the states of two neighboring nodes are actually independent. This is, again, a very strong assumption, but it will allow us to make some rapid progress analytically. So we'll be assuming that the average of 1 minus xi times xj is the same as the average of 1 minus xi times the average of xj, which is thus equal to 1 minus the average of xi times the average of xj. Yes. Now, if we take this and we plug that into the equations, what we would obtain then is the following. So we'll basically have that d by dt of this average of xi is going to be equal to beta times 1 minus the average of xi times a sum over the j's of aij times the average of xj. Now, the thing is that here what we'll be interested in the beginning of the dynamics, where initially we have a tiny fraction of infected people or infected nodes. And if we do so, we'll be looking at the linear dynamics, removing nonlinear terms, and the equation simplifies into d by dt of the average of xi is equal to beta times the sum of the j's of aij times the average of xj. So there's just one thing to consider here. Every time we looked at random walks, we either had the transition matrix or the Laplacian matrix, and those were exact equations. Here, in the case of epidemic spreading on contact networks, we can also get linear equations, but they would become approximations. And even more, instead of having the transition matrix or the Laplacian, what we have instead is the adjacency matrix. Where does this come from? It comes from the fact that in the case of random walks, we always have a conserved quantity. The number of walkers is conserved. While in the case of epidemic spreading, we have that the total number of viruses, the total number of infected people will actually be fluctuating in time, either growing or decaying. And hence, as we'll see, it will be associated to the fact that they would be having the adjacency matrix instead. Now, once we get this, we can write down, we can actually understand what would be the asymptotic behavior, because we can write a spectral decomposition of the adjacency matrix using the fact that we have an undirected graph, a symmetric matrix, that would give us a sum over the eigenvalues of lambda L, and then we would be having ULI, ULJ, and those would be the corresponding eigenvectors. And now, if you want to understand what is the dominant growth that's happening in this linear regime, you will basically have that the xi is going to be behaving like the exponential of beta times lambda 1 t, where lambda 1 is the largest eigenvalue of A, the dominant eigenvalue of the adjacency matrix, times the corresponding vector u1 I. So it basically means that asymptotically, the dominant contribution for in the linear regime would be coming from the largest eigenvalue, and that would be the one that determines how fast is the initial explosion of the number of infected people inside the population. Now, again, here it means that if you want to understand what is the impact of structure on this, on the initial growth of the number of infected people, you should basically consider a graph and then calculate what would be the corresponding lambda. Yeah. Now, something that can be done is just to look at simple situations and try to estimate what would be the dependency of this lambda 1 on, for instance, the degree distribution. Well, to do so, what we'll be assuming is that the graph is actually coming from, would be associated to a configuration model. And what we'll be assuming is that the graph is actually simply given by Aij prime. It's simply equal to this Ki, Kj divided by 2m. And if you remember, this is basically the expected number of edges between two nodes in the configuration model. So it means that we don't consider the configuration model itself, but more its average. We look at the average number of edges that would be happening between node I and j, assuming that the graph is distributed according to the configuration model, yes, and assuming that we can fix the degrees according to some prescribed degrees that we impose to the system. Well, if you take that adjacency matrix, it's relatively easy to show that the dominant eigenvalue lambda 1 is going to be equal to the average of k squared divided by the average of k. And indeed, if I consider the problem that's sum over the j's of aij prime, and I take as a vector kj, that would be my eigenvector. Yeah. Well, this is equal to a sum over the j's of ki times kj squared divided by 2m, yeah, which can directly be seen to be equal to the average of k squared divided by the average of k times ki. And so it means that indeed this is my dominant eigenvector, and that would be the corresponding eigenvalue that is associated to it. Yeah. And what does it tell us? Well, it tells us again that in situations when you have a contact network that is extremely heterogeneous, well, the average of k squared is going to be extremely large, and hence we're going to be a very, very steep increase of the number of infected people inside the population. We see again that the second moment of the degree distribution is indeed something that tends to favor the propagation of the virus in the very same way that we observed it in the case of metapopulation models. So what would be the intuition behind that? Well, this intuition behind it comes from the fact that if you have a node that has a very high degree, but this degree will participate twice in the way the epidemic spreading is diffusing. And indeed, if I have a node that has a high degree, like this, it will be very likely that it's going to be rapidly reached by the epidemics, because it has so many connections that it's very likely that it's going to be in contact with someone infected. Yes? And once it has been infected, it also has the possibility to infect many others. And so it means that when you have a high degree node, it will be infected very fast, and at the same time, it will also infect many other people. And you have the combination of these two things, being easily infected and infecting many people, actually can be combined, and they basically explain intuitively this k squared that we have here. The product of the degrees is actually what matters to explain how the effect of a certain node impacts on the propagation of a disease. Okay. Now, it basically means here that, well, the summary of what we've seen today is that, so when you have epidemic spreading, well, clearly the simplest modeling framework would be the case of the mean field, but you can actually enrich this mean field by incorporating networks in different ways, either with metapopulations or with contact networks. But I only scratched the surface clearly, and there exist many more and more refined models in the literature. And actually, these more refined models are used these days in order to understand and to model the way an epidemic like the one associated to COVID-19 is actually evolving in the course of time. And this is a really fascinating problem. And I just hoped that I gave you a good introduction to it. Thank you. So, hello everyone, and yeah, this is the end, as the name of this file indicates. This is the last video of this course. And well, obviously, first of all, I hope that you've enjoyed it, that you've enjoyed the discovery of all of these methods that exist in order to extract information from graphs and networks, but also these results that we've been showing about the relations that exist between network structure and dynamics on networks. What I wanted to do in this last video is just to emphasize the fact that what we've seen so far is just the surface of the field. And even if we've been considering relatively recent works, and many of the results that we've been talking about are maybe 10, 15 years old for most of them. Well, even if we've been looking at recent literature, we didn't have the time to investigate all of it. And for instance, we didn't look much into nonlinear dynamics on networks, which is a field where there are very beautiful results. I'm sorry for that, but if you're interested about these questions, well, just send me an email. I'm going to be very happy to send you some relevant references. Now, today, what I wanted to do is just to provide some perspectives on maybe some of the limitations and the ways to go beyond these limitations of network science as a network formalism. And to do so, I'm going to be covering some discussion that I had with some colleagues of mine, Martin Roswell and Ingo Scholz, that was published just a year or so ago. So let's start with a slide that is actually, I think, one of the first slides that I presented you in the first video. And that was a slide to show that networks are not reality. Networks are just an abstraction of reality, a language that can be used to basically synthesize all the aspects that are important to understand the connectivity of systems. And indeed, if we start here from the left to the right, we've been keeping only the nodes and the edges that are basically the key elements if you want to understand the way you can navigate a system by taking successive steps. Now, the thing is that you clearly know that the last 10 years have seen the emergence of big data, right? But not only are the data nowadays more and more rich, they are also more and more complex. And it happens many times these days that when you are confronted to a system, not only is it based on relational data that are clearly data that can be represented by networks, but also these data sets can be geometric in nature and also temporal. And so it means that when you adopt a network perspective, it could happen that you emphasize the relational aspect of the data and basically you neglect other aspects that don't fit into your modeling framework. Now, over the last 5 years, so I was involved in a series of conferences that are called Higher Order Models in Network Science, where different scholars from mathematics, physics, theoretical computer science discussed and tried to understand the limitations of networks as a model and maybe ways to improve on it and maybe to enrich it. And what I wanted to just to discuss briefly were the 3 different lines of research that have emerged in recent years in order to improve the network formalism. But the first one would be trying to address a first limitation, and that limitation is the fact that in networks, the basic building block are edges, and edges connect pairs of nodes. And it could be that in certain situations, well, the building blocks might involve more than 2 nodes. Another limitation is the fact that networks are constant in time. And indeed, like in all of the studies that we had, we considered the network to be constant and then looked at the possible dynamics taking place on this constant network. And finally, something that is also like implicit in what we've been doing is the fact that as soon as you had combinations of edges, you could build paths by looking at succession of incident edges. And that was a very powerful concept that allowed us to go from direct connectivity to indirect connectivity. But the thing is that in practice, it's not the case that all of these paths would be taken with the same probability. And as we'll see, sometimes you need to consider the path more than the edges when you want to model dynamics on networks. So let's start with binary interactions. Well, if you want to go beyond binary interactions, a very classical and very standard way to address this problem is to represent systems by means of hypergraphs. instead of graphs. And in a hypergraph, basically what you have is a set of nodes, and the nodes can be connected by hyper edges, and these hyper edges have a certain cardinality. So for instance, this E3 here would be a hyper edge involving 3 nodes, while this E2 would be an hyper edge involving 2 nodes, and so on and so forth. And if you think, for instance, at the collaboration network that is obtained by taking papers where people are collaborating on as co-authors, well, clearly the network of co-authors is not really a network. It's better suited to be described as a hypergraph, where for each paper that would be corresponding to a hyperedge of the number of authors in that paper. Now, there have been plenty of works in very recent years where people have been trying to generalize tools and methods from networks and graphs to the case of hypergraphs. And for instance, people have been looking at the notion of cut, people have been looking at the notion of community structure, clustering, and so on and so forth. In this example, for instance, they generalized this notion of cut to the case of hypergraphs. Now, another limitation that people have emphasized is the fact that networks are not constant. If you just think about contact networks that we discussed about just a few videos ago, well, clearly contact networks are dynamical entities, and the dynamics of edges are non-trigger processes. They are affected by non-stationarities and for instance, circadian rhythm, and so periodic. They have some periodic component to them, but also they are not independent. And typically, the emergence of an edge may have the effect of leading to the activation of another one. And there is a field of research called temporal networks, where people are looking at networks as dynamical entities, usually as some stochastic models. And well, if you're interested, so I was involved in writing a book about it. And if you want to have a look at it, I'm very happy to share it with you. Just send me an email. Now, besides this, so that would be a third dimension. And again, for temporal, for these temporal networks, you can generalize the concept of community detection, for instance. And in this case, then you may be interested in the way modules may be evolving in time. For instance, a big module could be separated into submodules. And so you really have a much more rich description that happens, that goes beyond the structure, but then really tries to understand the way these macro scale structures are evolving in time. Now, a third way in which people have been investigating possible generalizations of networks is by thinking about the notion of path. And indeed, when you think about it, when you start from the mean field, all of the nodes are connected to everyone, and all of the paths are possible. Then when you represent the system as a network, well, the network basically gives you some nodes and edges, and all of the edges, all of the paths that are made of a succession of these edges are eligible, yes? Now, a question that people ask is it the case that actually among all of these possible paths, are all of them actually explored in real data sets? Or are some of them used more often than others? Meaning that you again restrict the set of paths that are realistic from a modeling perspective. And just as a way to introduce the problem, so let's assume that you're interested in the way people are taking planes. In this case, that would be in the US. But you could consider a network of airports where you would have weighted edges that tell you the flow of passengers that go from one airport to another one. And if you were now to try to predict where a certain person would go after arriving on a node, well, if I go from here to there, well, from that node, I can go here or I can go there. And I'm going to take one of these edges with a priority that is basically proportional to the weight of that edge. And so, for instance, if I was to start from New York, I arrive in Chicago, well, then you would basically go to New York with a priority of 44% that is obtained from the strength of the link between Chicago and New York. And you would maybe go with 24% to San Francisco based on the strength of the link between Chicago and San Francisco. Now, if you look at real data sets, you get something that is very different. And indeed, what you observe that if you go from New York to Chicago, at the next step, the traveler will, with a very vast majority of the probability, go back to New York, which is very expected because it's just a return flight, right? And maybe he might go to San Francisco, but it's extremely unlikely that he would go to Atlanta, for instance, which is another hub, and there is no reason to do New York, Chicago, Atlanta. Just a few people do that. And here we see that if you really want to encode trajectories that would be associated to, for instance, human behavior, and human behavior can be approximated by a random walk. But as I said before, we are not random walkers. But then you may need to have models that account for the past to predict the future. And one way to do so is to adopt some non-Markovian modeling. And well, here is just one paper among several others where people tried to generalize notion from graphs to situations where the path would be the important elements of the connectivity, and it wouldn't be the edges anymore. And just as a second motivation, if you think about the way some information might spread between people, and let's take me as an example. If I receive some information from a family member, well, it's very likely that that information will go back to one of my family members as well, right? And so it means that where the information comes from should be helping you to predict where it's going to. Yeah? And this is something that can be done by using these non-Markovian models, but you wouldn't be able to do so with a Markovian model, as it would be implicitly assumed if you were to represent a system by a graph or a network. So these are the three main directions that people have been investigating over the last few years. And yeah, so there's still a lot of work to do. So you're very welcome to contact me if you find it interesting. And well, this last video is certainly not to say that networks are not good. And indeed, networks are a wonderful framework and extremely powerful by its generality. And in many situations, it can be used as a way to represent systems and also to extract some useful information from them. But I think that's important to keep in mind when you're a modeler of the limitations of the tool that you use. And here I wanted to finish this course just by emphasizing three of those limitations and three possible solutions in order to go beyond network modeling and to go to something that might be more realistic and more appropriate in certain situations. So as I said, this was the last video. I hope you enjoyed it. It was a pleasure to record them, and thank you very much. Bye.